So, hello everyone. So, today we are going to discuss about the AIET 4 NEET question and answer discussion. Okay. So, we are going to solve some important questions which you face it very difficult. Okay. So, let's start with the first. The first question is, a hydrocarbon contains 82.8% of carbon and rest hydrogen. The empirical formula is, so what we are asked to find out, we are asked to find out the empirical formula here, and the percentage of carbon and the hydrogen are given. So it is one of the very important question. Okay, to solve this. So first what we have to do, we have to take the element which are given here. So who are the elements which are present here? The elements that are present here are carbon and hydrogen. Then we have to take the percentage of the carbon and hydrogen present. So 82.8 is the percentage of carbon. And the remaining is hydrogen, right? So what we have to do? We have to subtract this 82.8 from 100. So 100 minus 82.8 gives 17.2. So this is the percentage of hydrogen. Okay. And the next one is we have to take the atomic mass of both the elements. So what is the atomic mass of both the elements? For carbon, the atomic mass is 12, and for hydrogen, the atomic mass is 1. Okay, what is the next step? We have to find out the number of moles present here. So how to find out the number of moles? Number of moles is equal to the given mass divided by the molar mass or the atomic mass, we can say. So for carbon, the number of moles is, the given mass is 82.8 and the atomic masses or the molar mass is 12. So what is 82.8 divided by 12? It is 6. Okay. And for hydrogen, it is 17.2 divided by 1. So it is 17.2. Okay. Then the next step is we have to find out the simplest ratio of the atoms. So the simplest ratio of the atoms has to be found out. So how to find out the simplest ratio? We have to divide any one of these number of moles. That is, you have to take the smallest number and divide it with that number for both the atoms. So 6.9 and 7.2 is here. 6.9 is the smallest number. So divide this by 6.9, you'll get 1. And 17.2 divided by 6.9 gives 2.5. Still the answer is in fraction. So what we have to do? We have to make it to the whole number, right? So we have to try multiplying by the number 2, 3 like that. So first let us try to multiply by the number 2 to get the whole number ratio. So to get the whole number ratio, multiply by the number 2. So if you multiply this by 2, you will get 2. And if you multiply 2.5 by 2, you will get 5. So we got the whole number. So how many carbons we are having? We are having 2 carbon and 5 hydrogen. So this is the empirical formula for the given question. So it is given in option B. Option B is the right answer for this question. Okay. Hope this is clear to you. Next we'll move on to the next question. So which of the following sets of quantum numbers are associated with highest energy? Which of the following sets of quantum numbers are associated with the highest energy? So how to find out? We have to find out the orbitals present in each option. Then we have to arrange them in the increasing order of their energy level. And we have to find out the answer. So you can use Aufbau principle to find out this answer. But before moving on to that part, we'll try to find out the orbitals present in each option. So the n value for the first option is 3. So it is n value is 3 and the L value is 2. N value is 3 and L value is 2. So if L value is equal to 0, then it corresponds to s orbital, right? If L value is equal to 1, then it is p orbital. If it is equal to 2, it is d orbital. If it is equal to 3, it is f orbital. This is how we have to take the respective orbitals. And here the L value is 2. So what it is? It is 3d orbital. Okay. And for the option B, n is equal to 3 and L is equal to 1. L is equal to 1 corresponds to which orbital? It is p orbital, right? So it is 3p. Then coming to the option 3, so it is 3s orbital, and option D, n value is 4 and L value is 0, so it is 4s orbital. So we know that from Aufbau principle, what is Aufbau principle? The electrons are arranged in the increasing order of energy levels. So what are energy levels? So we write the energy levels like this, right? 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, like this it goes on. These are the energy levels. And this is the increasing order of the energy level. So here they are asking the orbital and the quantum numbers which are associated with highest energy. So try to place these orbitals here. So 3D, so 3D is here. And in option B, we are having 3P, 3P is here, 3S is here, and 4S is here. So it is clear that 3D orbital is in the highest energy part. Okay. So option A is the correct answer for this question. Got it? Okay. Then we'll go for the next question. Using molecular orbital theory, compare O2 plus and O2 minus species and choose the correct option. So in the first option, it is given like O2 plus have higher bond order than O2 minus. And in option 2, it is given as O2 minus is less stable. In option C, it is O2 plus is diamagnetic while O2 minus is paramagnetic. In option D, both O2 plus and O2 minus are paramagnetic. So basically, we have to find out the bond order for both the species. So we can easily find out the bond order using a trick, right? So you can use this table. This is the trick table to find out the bond order using the total number of electrons present in the species. Okay. For example, in case of O2 plus, how many electrons we have? For one oxygen, the atomic number is 8. Here we are having two oxygen, right? So for both the oxygen, 8 plus 8, we are getting 16. And here positive charge is there, means the oxygen has lost one electron. So what is the answer? 16 minus 1 is equal to 15. So 15 is the total number of electrons present in O2 plus. Okay. So if the number of electrons is equal to 15, then what is the bond order? Bond order is 2.5. We have to fix this 14 as the standard value. For 14, the bond order would be 3. If you are going to 13, 12, 11 and 10, you have to subtract 0.5, 0.5 to get the bond order. And for 15, 16, 17, 18 also, you have to do the same. Okay. So if the number of electrons is reached out to be 15, then the bond order is 2.5. For O2 plus, the bond order is 2.5. And for O2 minus, what is the calculation? So again, for O2, we have 16 electrons. If it is minus, O2 has gained one electron. So we have to add that electron to the 16. So finally, we get 17 electrons. So if the number of electrons is equal to 17, then the bond order is 1.5. So 2.5 is the bond order of O2 plus and 1.5 is the bond order of O2 minus. Okay. So this is the thing. And coming to the options, in the first option you see O2 plus have higher bond order. That is 2.5 is higher than 1.5, right? So that is the correct option. But they are asking us to find out the incorrect statement. So we have to go to option B. O2 minus is less stable. So how to find out the stability? Using the number of electrons present in bonding orbital and antibonding orbital. So for O2, in the O2 diagram, in the 1s molecular orbital, sigma star 1s, we have 2 electron. And in sigma star 2s, we have 2 electron. And in the pi star 2px and pi star 2py, we would have 1 electron each. So this is the diagram. This is the number of electrons present in antibonding orbitals for O2. Okay. So how many electrons totally? 2 plus 2 plus 2. It is 4. For O2, we have 4 antibonding electrons. Okay. In case of O2 minus, we are adding one more electron. That one more electron goes to this orbital. So now we are getting, for O2 minus, we are getting 5 antibonding electrons. We are getting 5 antibonding electrons. In case of O2 plus, what we will do? We'll remove this one electron. This electron will not be there. And we'll remove this electron also. So how many electrons we would have? Sorry, 1, 2, 3, 4, 5, 6, 7, right? So here we'll have 7 and here only we'll have 5. 5 antibonding electrons will be present. So if the number of electrons present in antibonding orbital is greater than the number of electrons present in bonding orbital, then the resulting species is less stable. Resulting species is less stable. So you see here, O2 minus is having 7 antibonding electrons, means that is less stable and it is the correct statement. Now we have to see option C. O2 plus is diamagnetic while O2 minus is paramagnetic. So how to find out the magnetic nature? So there are two different types of magnetic character, paramagnetic and diamagnetic. Okay, but now for paramagnetic, so which species will fall under paramagnetic character? All the odd number of electrons containing species, including 10 electron species and 16 electron species will fall under paramagnetic. Now except 10 and 16 with even number falls under diamagnetic. Okay. So in O2 plus how many electrons we are having? We are having 15 electrons. 15 electrons means it is an odd number. So O2 plus is paramagnetic in nature. Okay. And O2 minus, you see, we have 17 electrons. Again, 17 is an odd number. So O2 minus is also paramagnetic in nature. But in the statement, you see, O2 plus is given as diamagnetic. So that is the incorrect statement, which is the correct answer for this question. Got it? And for option D, both are paramagnetic. That is the correct answer, which we have seen just. Clear? Okay. We'll move on to the next question. Which of the following compound of xenon has pyramidal geometry? This is one of the very important questions. You should know the structure to find out the thing, that's all. But it is very easy. So these are the structures of all the 4 components given here. So in option A, XeOF4 is there. So XeF4OF4 is having square pyramidal geometry. And XeF2 is having linear geometry. And here XeO3 is having pyramidal structure and XeF4 is having square planar structure. Okay. So the one which has the pyramidal geometry is XeO3. XeO3 is having the pyramidal geometry. So option C is the correct answer for this question. Okay. Then we'll go for the question number 61 in your question paper. The number of antibonding electrons present in O2 molecule ions. Number of antibonding electrons present in O2 molecule ions. So this is the MO diagram, that is the molecular orbital energy level diagram for O2 molecule. And here you are asked to find out the antibonding electrons. Antibonding means the electrons which are present in the higher energy level orbital. Here it is represented using a star. You see, these are the antibonding electrons. Okay. So we do have oneness here, but oneness mostly it won't be represented in the diagram. So we do have oneness atomic orbital, which has 2 electrons each. And here also we have 2 electrons, and when these 2 electrons combines, they form 2 molecular orbitals. So we'll have 2 plus 2, 4 electrons, and this is the sigma star 1s, and this is sigma 1s orbital. So now you can find out the total number of antibonding electrons present in O2 molecule ion. Okay, so can you find out? So what is the answer here? So this is a star orbital which is antibonding. Here it has 2 electrons, and here in sigma star 2s we have 2 electrons, and here pi star 2px1 and pi star 2py1. So totally 2 plus 2 plus 2, 6 electrons we have. Okay, so 6 is the answer for this question. Now coming to question number 63. So statement 1 and statement 2. Two statements are given. We have to find out the correct answer. What is statement 1? The radius of second orbit of helium plus is equal to that of the first orbit of hydrogen. And statement 2 says like this. The radius of an orbit in hydrogen-like species is directly proportional to n square and inversely proportional to z they are as given. So what is the relation we know? We know that radius of the nth orbit is directly proportional to the n square and inversely proportional to z. So what is n? N is the number of the orbit, number of the shell we can see. And z is the atomic number. Okay, so this is the relation. In statement 1, they have given radius of the second orbit of helium. So for helium, what we have to do? For helium plus, the radius is find out like this. It is directly proportional to, the radius number is 2, the n value is 2. So it is 2 square, and the atomic number of helium is 2. So 2 square is 4, and 4 by 2 is 2. It is equal to that of the first orbit of hydrogen. So for hydrogen, how to find out the radius? For hydrogen, the electron is present in the first orbit. So it is 1 square, and the atomic number of hydrogen is also 1. So 1 square by 1 is 1. So what they are saying? For hydrogen it is 1, and for helium plus it is twice that of the hydrogen, that is 2. So statement 1 is correct. Statement 1 is correct. Okay. Now coming to the second statement. The radius of an orbit in hydrogen-like species is directly proportional to n square and inversely proportional to z. So statement 2 is correct, but you see here, it is twice that of hydrogen is twice that of the helium plus. I am really sorry. So here it is given it is equal to that of the hydrogen. So it is incorrect, right? So actually the helium radius is twice that of the hydrogen. But here it is given as it is equal to that of the first orbit. So statement 1 is incorrect, but statement 2 is correct. So option D is the correct answer for this question. Got it? Oh, sorry. So option D is the correct answer. Then coming to question number 67. Based on the first law of thermodynamics, which one of the following is correct? So option A, for an isochoric process, delta U is equal to minus. We have to check one by one. Okay. So what is isochoric? Isochoric means delta V, that is change in volume, is equal to 0. And we know that W is equal to minus P delta V. If delta V goes to 0, work done is also 0. So from the first law of thermodynamics, what is first law of thermodynamics? Delta U is equal to Q plus W, right? So here W goes to 0. So delta U is equal to Q. But here it is given as minus. So this cannot be the answer. Then for adiabatic process, delta U is equal to minus W distance. So what is adiabatic? Adiabatic Q is equal to 0. Q is the heat exchange between the system and the surrounding, right? So Q will be 0 there. So from the first law of thermodynamics, delta U is equal to Q plus W. If Q goes to 0, delta U is equal to W, right? But it is given as minus W. So it is also incorrect. Then for isothermal process, delta T is equal to 0. Isothermal means same temperature, right? So delta T is 0. So then from first law of thermodynamics, or we are also having one more equation, that is delta U is equal to NCV delta T. So this is the relation we have for delta U and delta T. Here if delta T goes to 0, delta U is also 0. Delta U is 0, substituting this in the first law of thermodynamics, that is delta U is equal to Q plus W. If delta U is equal to 0, then Q is equal to minus W, right? So, but here in the relation you see Q is equal to plus W. So, again it is the incorrect state. Then for cyclic process. So, the cyclic process, for all the cyclic process, the state function like internal energy, enthalpy, everything is equal to 0. So, delta U is a state function. So, delta U plus QW, here delta U goes to 0. So, Q is equal to minus W. So, for all the cyclic process, state functions like delta U goes to 0. So, from this, we are getting this Q is equal to minus W as the correct relation, which is given in option D. Option D is the correct answer for this question. Okay. Hope this is clear to you all. Then we'll go for the next question. Question number 70. 10 gram of a gas at ST at standard temperature and pressure occupies 5 liters. The temperature at which the volume becomes double for the same mass of gas, keeping the pressure constant is. So what is given here? Here, volume is given. V1 is equal to 5 liter. V1 is equal to 5 liter. And the temperature at which the volume becomes double. So what is the final volume? Final volume is gets double, right? So it is 10 liter. Okay. And the initial temperature, T1. So the standard temperature and pressure condition it is given. So the standard temperature is 273 Kelvin. And we are asked to find out the temperature, that is a final temperature at which the volume becomes double. So we are asked to find out the T2 value. So how to find out this? So we know this Charles law, right? So from Charles law, V1 by T1 is equal to V2 by T2. So what is V1? It is 5 liter and V2 is 273 Kelvin. T1 is 273 Kelvin. V2 is 10 liter and T2 is us to find out. So what is T2? T2 is equal to 10 into 273 divided by 5. So what we are getting? We are getting 2. So 2 into 273 is equal to 546 Kelvin. So this is the final temperature. Very easy, but it is very important. Okay. So option C is the correct answer for this question. Now let's move on to the next question. It is question number 71. The rates of diffusion of two gases A and B are in the ratio of 1:4. And those of B and C in the ratio of 1:3. The rates of diffusion of C with respect to A is. What they have given? The rate of diffusion of two gases, that is RA by RB is equal to 1/4. What is next? RB by RC is equal to 1:3. So it is 1 by 3. Now we are asked to find out the rate of diffusion of C with respect to A. That is, we have to find out RC by RA we are asked to find out. Okay. So to solve this, what we can do, we can multiply these two, RA by RB and RB by RC, we can multiply. So on multiplying these two, that is RA by RB getting multiplied by RB and RC, right? So what we get from here, 1 by 4 into 1 by 3. So it is nothing but 1 by 12. Okay. Or that is RA by RC is 1 by 12. But we are asked to find out RC by RA, right? So what it is? It is 12 by 1, or simply we can say it is 12. So the rate of diffusion of C with respect to A, that is RC by RA is 12 by 1, which is equal to 12. So option B is the correct. Okay. Now moving on to question number 72. Two gases which do not react confined in two separate vessels of equal volume exert 100 mm and 300 mm of pressure respectively. If both the gases are placed in one vessel, the resultant pressure will be. So both the gases are present in one vessel and we are asked to find out the resultant pressure. And the two different systems pressures are given. So we know that it is very easy. The total pressure is equal to the sum of the partial pressure, right? That is PA plus PB. The total pressure is equal to the sum of the partial pressure. So two pressures are given. One is PA and the other one is PB. So PA is equal to 100 and PB is equal to 300. So the total pressure will be 400. Okay, that's an easy question, right? So the answer is option A. 400 mm is the answer. Okay. Next we'll go for question number 74. Which of the following statements is the best description of the behavior of bromine in the reaction given below? So H2O plus Br2 gives HOBr plus HBr. And option A is proton acceptor only. Option B says that it gets oxidized as well as it gets reduced. And in option C only gets oxidized. And in option D, it says that bromine only gets reduced. So to solve this question, we have to find out the oxidation number of all the bromines present in this reaction. So what is the oxidation number? H2O plus Br2 gives HOBr plus HBr. Okay. Okay. So what is the oxidation state of bromine here? Here it is 0 because it is present in the elemental form, right? So in the elemental form, the oxidation state is 0. And in HOBr, what is the oxidation state? So to calculate the oxidation state of bromine, we take this as X. And for oxygen, it is -2. For hydrogen, it is +1. So +1 plus -2x plus -2 and plus x is equal to 0. And x is equal to 2 minus 1, which is equal to +1. So the oxidation state of bromine is +1 in this. And in case of bromine, here for hydrogen, it is +1. So obviously for bromine, it is -1, right? So this is the oxidation state of all the bromine. So bromine is going from 0 to +1 in one of the product, which is oxidation. And in the other product, bromine is going from 0 to -1, that is reduction. So what is the answer? Bromine gets oxidized as well as it gets reduced. Okay. Now next we'll go for the next question. In your option B is the correct answer for this question. Go for next question. That is question number 75. Which of the following arrangements represent the correct order of least negative to most negative electron gain enthalpy for the given species? So what is electron gain enthalpy? Electron gain enthalpy is the amount of energy released when an atom gains an electron, right? So in the periodic table, the electron gain enthalpy becomes more negative across the period. That is the electron gain enthalpy. Electron gain enthalpy increases across the period and the electron gain enthalpy decreases on moving down the group. So here 5 elements are given. One is calcium. Calcium is here. Calcium is in the 4th period. And aluminium is present in 3rd period of P block is here. And carbon belongs to the 2nd period. So here comes carbon. And oxygen also, after nitrogen, oxygen comes, it is also in the 2nd period, and fluorine is here in the 2nd period. So the high value of electron gain enthalpy, that is the more negative value of electron gain enthalpy is for fluorine because it increases, right? Fluorine is having the highest value. Then it is oxygen, then it is carbon. But on moving down the group, it decreases. Means aluminium is having the highest value than calcium. So next comes this aluminium, then this calcium. So it is given in option D, right? Calcium, aluminium, carbon, oxygen, and fluorine. So this is the answer for this question. So coming to the next question, question number 76. The oxidation number of carbon in the given compounds. Very easy, right? So in CH3OH, how to find out? So in CH3OH, you have to find out the oxidation number of carbon. It is X. And for hydrogen, it is +1. We are having 4 hydrogen. You can put +4. And for 1 oxygen, it is -2. It is equal to 0. So X is equal to -4 plus 2. And X is equal to minus. Okay. And for CH2O, what is oxidation state of carbon? Take this carbon as X. And for each hydrogen, put +2. And for each oxygen, it is -2. It is equal to 0. So X is equal to -2 plus 2 gets cancelled. So X is equal to 0. And for HCOOH, for carbon, it is taken as X. For hydrogen, it is +1. For 2 oxygen, we can put -4. And one more hydrogen is here, put +1, which is equal to 0. And X is equal to +4 -2. So X is equal to +2. And the next one is C2H2. For carbon, it is 2X. And for hydrogen, it is +2. So 2X is equal to -2. And X is equal to -1. So -2, 0, +2, and -1 is the answer. It is given in option A. Okay. Fine. Next, we'll go for the next question. Question number 79. Which of the following sets of quantum number is correct for an electron in 4f orbital? So for 4f orbital, n value is equal to 4. Okay. And L value is equal to 3 for f orbital, right? L value is equal to 3 for f orbitals. We have already seen, no? If L is equal to 0, it is s orbital. If it is 1, it is p orbital. If it is 2, it is d orbital. And if it is 3, it is f orbital. So for f orbital, the L value is equal to 3. So for each L value, the M value ranges from minus L to plus L, right? So M value will be equal to minus 3, minus 2, minus 1, 0, plus 1, plus 2 and plus 3, right? Ranges from minus L to plus L. And S value would be like minus half or plus half, any one. So check with option A. So if N is equal to 4, L is equal to 3. And plus 1 is the M value given here. So it is plus 1 is present in the magnetic quantum number. And S value is plus half. So everything is there. So option A is the correct answer. You can cross check with the other options also. So here you see for a given value of L value is 4. It cannot be 4. It is 3, right? So this cannot be the option. And here N and L values are equal and correct. S value is also correct. But M value is given as plus 4. So plus 4 doesn't fall under this magnetic quantum. So it cannot be the option. And in option D, for 4f orbital, N value is 4. N value is itself wrong here. So option D is also not the answer. So option A is the correct answer for this. Okay. Then coming to question number 18. The ratio of radius of the fourth orbit of hydrogen and the third orbit of lithium 2 plus is. So what we have to find out? To find out the radius of both these. That is for hydrogen and for lithium. So what is the relation we have to use? Rn is directly proportional to n square divided by Ez. So for hydrogen, fourth orbit of hydrogen. So R4 of hydrogen is equal to or proportional to 4 square divided by the atomic number of hydrogen is 1. So 4 square is 16, right? So it is 16 by 1, which is equal to 16. And the third orbit of lithium 2 plus. Third means R3 of lithium 2 plus. So R value is 3. So 3 square. The atomic number of lithium is 3. So 3 square is 9. 9 by 3. What is 9 by 3? 9 by 3 is 3. So what is the ratio? R4 of hydrogen by R3 of lithium 2 plus is equal to 16 by 3. So 16 is to 3 is the correct answer and option C is the answer for this. Okay. Then coming to the 82nd question. 82 says that the ratio of the energy of a photon of wavelength 200 nanometer to that of 400 nanometer is. So we have to find out the ratio of energy. So what is energy? Energy is equal to the relationship between energy and wavelength is E is equal to hc by lambda, right? E is equal to hc by lambda. So here from this relation, it is clear that energy is inversely proportional to the wavelength. Okay. So what is E1? E1 is equal to 1 by lambda 1 and E2 is equal to 1 by lambda 2. So what is E1 ratio? E1 by E2, it is equal to lambda 2 divided by lambda 1, right? So what is the wavelength lambda 1? Lambda 1 is equal to 200 and lambda 2 is equal to 400. So 400 nanometer divided by 200 nanometer gives the answer 2. So option D is the correct answer. This is the ratio of the energy of a photon of both the waves. Got it? Then coming to question number 84. The maximum kinetic energy of photoelectrons ejected from a metal when it is irradiated with radiation of frequency 2 into 10 power 14 is 6.63 into 10 power minus 20 joule the threshold frequency of the metal is. So what we have to find out? We have to find out the threshold frequency. So what is threshold frequency? The threshold frequency is represented by mu naught. Mu naught we have to find. So we know that the kinetic energy, that is half mv square, is equal to h into mu minus mu naught. Okay. So kinetic energy is given here as 6.63 into 10 power minus 20 joule. But we have to represent in terms of per second, right? So convert this joule to 1 joule is equal to 1 kilogram meter square per second square. So this is the kinetic energy. It is equal to h. H is the Planck's constant, right? The value of Planck's constant is 6.63 into 10 power minus 34 kilojoule meter square per second. And what is the frequency mu given here? Frequency value is 2 into 10 power 14 minus mu naught we are asked to find out. This is the threshold. Got it? Now how to solve this? 6.63 to 10 power minus 20 divided by, take this term here, the 6.63 into 10 power minus 34, which is equal to 2 into 10 power 14 minus mu. Okay, so you can cancel this. You can cancel this. If we cancel this, we'll get 10 power minus 14 in the denominator. Take this to the numerator. You will have 1 into 10 power plus 14 and bring this 2 into 10 power minus 4 to the other side. Becomes negative, right? So it is minus 2 into 10 power 14, which is equal to minus mu naught. And 1 into 10 power 14 minus 2 into 10 to the power 14 is nothing but minus 1 into 10 power 4. 2 minus 1, right? That is 1 minus 2, which is equal to minus 1, and it is equal to minus mu naught. So minus mu naught, minus minus gets cancelled. So from this, what we are getting? From this, mu naught is equal to 1 into 10 power 14, and here the unit is per second. Here it will, you'll have minus 1 now on cancelling out this. So it is per second. So the answer is 1 into 10 power 14 per second. That is option D is the answer for this question. Okay. Now coming to the next question, question number 86. Given that the abundance of isotopes Fe54, Fe56 and Fe57 are 5%, 20% and 5% respectively, the atomic mass of Fe is. So 3 isotopes of iron are given and their percentages are given, and we have to find out the atomic mass. So what is the formula to find out that? Atomic mass of iron is equal to, we have to take the average of all these 3, right? How to take the average? The percentage of each thing into the atomic mass divided by 100. So what is the percentage of the first species? It is 5. And 5 has to be multiplied by the atomic mass, which is 54. Like that, 90 into 56 plus 5 into 57. 57. The whole divided by 100. So sum of the percentage and atomic mass relation divided by 100 is the relation to find out the atomic mass of iron. So what is the answer? 5 into 54, it is 270, and 90 into 56, you will get 5040, and 5 into 57 is 285 divided by 100. So on solving this, we get 55.95 unified mass as the answer for the atomic mass of iron. Okay, where it is given 55.95, it is given in option B. So just you have to multiply the atomic mass and the given percentage and sum up all the thing and divide by the number 100 to get the percent. That's So option B is the answer to this question. Now coming to question number 87. The increasing order of the ionic radii of the given isoelectronic species is. So how to find out the ionic radii? Ionic radii is inversely proportional to the atomic number or the charges, right? You see here, all these are the same number of electrons containing species. So we have K plus, S2 minus, A2 plus, and Cl. So we can arrange this according to the charge. So K plus and the calcium 2 plus, Cl minus, and S2 minus. So these are the species, right? The relation which you have to use to find out the sizes, the ionic size is inversely proportional to the atomic number. So since all the species have same number of electrons, go with the atomic number. Atomic number of sulfur is 16. Atomic number of chlorine is 17. For potassium it is 19 and for calcium it is 20. So the one which is having the highest atomic number will have the smallest size. So who is the species which has the highest atomic number? Calcium 2 plus is having the highest atomic. So it is having the smallest size. And then potassium, Cl minus and S2 minus. Okay. So what is the answer for this question? They are asking the increasing order, right? Increasing order means smaller size to bigger size. That is calcium, potassium, Cl minus, and S2 minus, sulfide ion. So it is given in option D. So this is the increasing order of the 4 given species of size. Okay. Now let's move on to the next question. The IUPAC name of the given compound is. It is very easy, but we have to find out the locant rule here. Locant rule means on adding the number of all the carbons to which the substituents are attached, you should get the least possible value, right? So start with chlorine. So 1, 2, 3, 4, 5, and 6. So what you are getting? Chlorine is attached to carbon number 1, nitrogen is attached to carbon 2, and methyl group is attached to carbon number 4. So 1 plus 2 plus 4 is 7, right? And when you start with the nitrogen and go with clockwise direction, you will get 1, here 2, and here 3, 4, 5, 6, you will get. And when you add all these numbers, that is 6, 1, and 3, you will get the number value as 10, right? That is very big number. So that cannot be the answer. And when you start with methyl, you will get 1 here, and 2, 3, 4 for chlorine, and 5 for nitrogen. And 1 plus 4 plus 5 we will get. So it is also again 10. So it is also not the answer. So what we have to do, we have to start with chlorine. So while starting with chlorine only, we are getting the smallest possible number following this locant rule. And this is the correct way of numbering. So it is, we can remove the remaining part. Just wait a second. All these are the incorrect way of numbering. So what is this? Cl. Cl is called as chloro, and this is nitro, and this is methyl. So while naming the compounds, we have to go according to the alphabetical order, right? For IUPAC nomenclature. So C comes first there, and M comes next, N comes the third one. So 1 chloro, 4 methyl, and 2 nitrobenzene is the correct answer. So where it is given in option B. 1 chloro, 4 methyl, 2 nitrobenzene. Got it? So the next question, one more question is also with the IUPAC. So what is the IUPAC name? So basically to solve this, we have to start numbering from the longest highly substituted chain that is propane. Okay, so propane is the longest substituted chain, right? And how to number this from left to right or right to left? Alcohol should get the first priority. Since bromine is the substituent and alcohol is the functional group, functional group should get the first preference, right? So OH attached carbon should get the first preference. So 1, 2, and 3. And the name of the substituent is bromo. So how to name this? D-bromo, 1 phenyl. This group is phenyl, right? So it is C6H5, which is called as phenyl. So 3 bromo, 1 phenyl, because according to the alphabet, B comes first and P comes next. So 3 bromo, 1 phenyl. Since 3 carbons are present in the parent chain, it is propane, and in the first position, alcohol is attached. So 1 all, 3 bromo, 1 phenyl, propane, 1 all is the correct answer for this question. Okay, fine. Now moving on to question number 91. 4 successive members of the first row transition elements are listed below with their atomic numbers. Which of them is expected to have the highest third ionization enthalpy? What is third ionization enthalpy? What is ionization enthalpy? The energy required to remove the electron from the outermost shell is called as ionization enthalpy or energy. So the energy required to remove the first electron is first ionization enthalpy, second electron is second ionization enthalpy, removing the third electron is third ionization enthalpy. So after the removal of the second electron, each species would attain this configuration. Vanadium 2+, chromium will be 2+, manganese also there in 2+ configuration, iron is also there in 2+ configuration. In this configuration, what is the electronic configuration for each species? So normally the vanadium atomic number is 23. The electronic configuration is 3d3 and 4s. And for chromium it is 24. So it is 3d5 and 4s. This is the exception, right? So since this d orbital is attaining the half-filled configuration, one of the s electron will jump to the d orbital to get this to give this configuration. Otherwise, the configuration would be 3d4 and 4s2. Okay. And for manganese, it is 3d5 and 4s2. And for iron, we have 26 electrons. So it is 3d6 and 4s2. If it is 23, you will have 3d3. If it is 24, you will have 3d4. But since this d5 is the stable electronic configuration, electron jumps here. And for 25, you have d5. And for 26, you will have d6. So these are the configurations. And if 2 electrons are removed, what is the configuration of this vanadium? 2 electrons are removed from the s orbital. So you will have 3d3 here. And if 2 electrons are removed for chromium, what we will have? 2 electrons are removed, and here we will have 3d4 configuration. And for manganese, if this 2 electron from s orbital gets removed, we'll have 3d5. And for iron, if 2 electrons are removed, we'll have 3d6. Now, which one is expected to have the highest third ionization? To solve this, you have to take the number of electrons present in the d orbital. In case of vanadium, so how many d orbitals we have? We have 5 d orbitals, right? In case of vanadium, we are having 3 d electrons. In case of chromium, we have 4. In case of manganese, 5. And in case of iron, it is 6. Coming to the manganese 2+. Since manganese 2+ has 5 electrons in its d orbital, it is in half-filled electronic configuration. Half-filled electronic configuration means it is in the stable electronic configuration. The stable species cannot be disturbed, right? And more energy is required to remove the electron from the more stable system. So, third ionization energy value for Mn2 plus will be 4. Okay. So option C is the correct answer. While the other species, you see, others are having the partially filled d orbital. So they are less stable only, and we can easily remove the electron from the less stable system. Got it? So manganese 2 plus manganese is the answer for this question. And coming to question number 92. The correct order of the first ionization potential among the following elements, beryllium, boron, carbon, nitrogen, and oxygen is. So all the 5 elements belongs to the second period, right? All these are second period. Second period starts with lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, neon. But these 5 elements are given from the second period here in this question. So you might have studied in your class that the correct order of first ionization across the period, ionization energy increases. This is the general trend you might have studied. According to the general trend, oxygen should have the highest ionization energy value. Then comes nitrogen, carbon, boron, and beryllium. This is the general trend. But for second period elements, there is an exception, right? For second period elements, we do have the exception. Where we have this exception? We have for beryllium and boron and for nitrogen and oxygen. Why this exception? For beryllium and boron, this exception is because of the penetration effect of the orbital. So here for beryllium, the configuration is 2s2, and for boron, it is 2s2 and 2p1, right? So 2s2 is completely filled, and the last electron is present in the 2p orbital, which is partially. S electrons will be more penetrated than the p electron, than D, than F. The one which is more penetrated, or the one which is more closer to the nucleus, and the electron which is present inside the s orbital is very difficult to remove. Okay, so because the attraction between that s electron and the nucleus is more, so more energy is required to remove the electron from the s orbital. So the removal of p orbital becomes easy, but s electron is difficult. So you have to supply more energy for beryllium than boron. So it goes in this way. Boron would be having less value than beryllium. And coming to nitrogen and oxygen, the electronic configuration of nitrogen is 2s2, 2p3, and for oxygen is 2s2, 2p4. So in case of nitrogen, in 2p orbital we have 3 electrons, and in case of oxygen, 2p orbital we have 1, 2, 3, 4 elements. So oxygen is partially filled and nitrogen is half filled. So which configuration is more stable? Half filled configuration is more stable, right? So the energy required to remove the electron from the more stable configuration is more. So means nitrogen requires the highest energy than oxygen. And in between carbon is there. So this should be the correct order. So this is that exception. So where this option is given, first boron, then beryllium, carbon, oxygen, and nitrogen. It is given in option A, right? So option A is the correct answer, correct order for the first ionization potential among the following elements. Got it? Moving on to question number 94 of the paper. The correct IUPAC name of the following form. So first, to find out the IUPAC name in case of open chain system, we have to find out the longest chain, that is the parent chain, right? And here we have 2 chain. In case of this straight chain, 1, 2, 3, 4, 5, 6, 7 carbon atoms are there. And in this chain, 1, 2, 3, 4, 5, 6 are there. But in the 6 carbon containing chain, we have double bond present in it. So double bond is the functional group. So functional group containing chain should be taken as the parent chain. Okay. And it should be given the first priority also. So this is carbon 1, 2, 3, 4, 5. And this chain is taken as the parent chain, and numbering is done in such a way that the functional group gets the first preference. So 1, 2, 3, 4, 5, 6. So now to the third carbon, one alkyl group is attached, and this alkyl group has three carbon containing alkyl group is called as propyl. And to the fourth carbon, one alkyl group is attached, and in this alkyl group we have two carbon, and two carbon containing alkyl group is called as ethyl. So alphabetically, E comes first and P comes next. Okay, so starting the name, substituents should get the first priority while naming. So 4 ethyl and 3 propyl is the substituent. That is a prefix. Then comes the root word. Root word is 1, 2, 3, 4, 5, 6, right? 6 carbon containing chain. So it is hex. And between 1 and 2, we are having the double bond. So 1 E. So 4 ethyl, 3 propyl, hex, 1 E. So option A is the answer. So 4 ethyl, 3 propyl is the prefix, and hex is the root word, and ene is the suffix. An IUPAC name contains all these things, right? Prefix plus root word plus suffix. So option A is the answer. And coming to question number 96, an open container contains certain gases. An open container contains certain gases is heated from 27 to 127 degree Celsius. What mole percentage of the gases escaped from the container? Okay. What we have to find out? We have to find out so here you see the two different temperatures are given. The one is temperature T1 is 27 degrees Celsius and the T2 is 127 degrees Celsius. So convert this into Kelvin. So 227 plus 273 is equal to 300 Kelvin, and 127 plus 273 is equal to 400 Kelvin. So what we are asked to find out? We are asked to find out the mole percentage of the gas escaped from the container. So since it is an open container, the pressure and the volume, they are same. In case of open container, the pressure and volume remains same, right? So from an ideal gas equation, which is PV is equal to nRT, since both the pressure and volume, they are same, the number of moles is a constant, and R is also a gas constant here. And but we have two different systems. So we have N1, T1 for the first system and N2, T2 for the next system. So pressure is constant, volume is constant, number of mole is constant for that particular system. So N1 and N2 we have, and R is a constant value and T is the variable for both the systems. So N1 T1 is equal to N2 T2 we can say. Okay. So N1 into the temperature T1 is 300 is equal to N2 into the temperature is 400. So what is N2? N2 is equal to 3 by 4 of N1. What it is? 3 by 4 of N1. That is 25%, right? N2 is equal to 3 by 4 of N1 means it is N2 is 75% actually. 3 by 4 of N1 percentage of N1. So number of moles of gas escaped from the container would be 25. Because to find out the percentage of mole escape, what we have to do? We have to divide, right? N1 minus 3 by 4 of n1 divided by n1 into 100, right? So it is equal to 1 minus 3 by 4. You have to go with it. It will give 25%. Since n2 is 25% of n1, n1 is percentage of mole escape from the container is 25. So option A is the answer for this question. Okay. So hope all the questions are clear to you, and the questions which we have discussed, they are very important questions. Okay. So thank you everyone.